Hello everyone, welcome to the second part of our cryptology discussion. So last time we talked about block ciphers, so today we are going to talk about hash functions. So let's start by giving a definition of a hash function. A hash function h is a keyless algorithm that takes a variable length input x and returns an output y of fixed length n, and we call this length message digest length, and of course the output we call it the message digest. So idea is simple. You can have a variable length input, but the output is always fixed and it is a very small amount of data. But this is a definition of a hash function. In order to be a hash function to be a cryptographic hash function, we wanted to have some properties. So actually the following three properties should be satisfied by a hash function to be called a cryptographic hash function, and they are preimage resistance, second preimage resistance, and collision resistance. So I will briefly mention what they are and give some examples why we need such properties. But at the end, what we are trying to have is that we want a hash function to behave like a random function. And this will make sense at the end. So let's start with the preimage resistance. So first property we need to satisfy is preimage resistance. And idea is as follows. Given an output y, it should be hard to find any input x such that hx equals to y. So we are trying to define a one-way function in this sense. So a generic attack would require around 2 to the n operations because the output is n bit. So if you try 2 to the n different input here, we expect around 1 output to be equal to y. So why do we such a thing? Why do we need such a property? Actually, this property is used for many different purposes, but basic example would be about storing passwords. So in a password file or in a database where you keep passwords, people what did initially was to store the username and password of the users. Of course, this was a bad idea, and a lot of databases leaked in the past, and also they leak today. So when such a thing happens, all of the username and passwords leak too. So this is a very bad scenario. But if you store it like this, if you just store the username and hash of the password, then somebody who captures the database would know your password, but they would know the hash of your password. So if the hash function is preimage resistant, knowing the output y would not give them your password x. So this is one reason why we need a preimage resistance. But this is also sufficient to verify a password. So assume that you want to log in the web page. So the web page also does not store your password, but whenever you want to log in, you type your password, they compute the hash of it and check if it matches the value they stored in the database. So regardless of they store it as a password or hash of it, you can always log into your account. But when it leaks, when an attacker that captures the password file or the database, they have to find the preimage. So for this reason, you shouldn't have easy to guess passwords, because they can try easy passwords and capture your password. Of course, this is just a basic example. In real life, we also add some random value to the end of your password that we call salt. And instead of computing the hash of it, we keep taking the hash of the output like thousands of times to make it harder for the attacker to capture a password. So a good thing to remember here is that you can check if a service keeps your password in the database as a plain text like this, or if they keep the hash of it as follows. Just click the link that says I forgot my password, and if they send you your password back with an email, this means that they are keeping your password like this. So this is a very bad thing, and you should never use a password that is kept in this way in another place. But if they send you a link to create a new password, this means that they are keeping the hash of your password, so they don't know your password too. So they just send you a link to create for yourself. Unfortunately, there are still a lot of web pages that keep your password as a plain text like this. So this is a good way to check if they're doing it. Next thing is the second premise resistance. This time you are given an output Y and the input X. So you know X1 and its hash output Y. Now it should be hard to find any other input X2 such that it also gives you the same output. So you might think that why this is the case, since the input space is almost infinite, but the output space is limited because we choose the message digest length as n bits. So there are at most 2 to the n different outputs. But since we didn't limit the input space, you are mapping a very huge space into a small space, so there will be collisions like this. But we want it to be hard to find such a collision, but in this scenario, we will talk about collision resistance in a minute, but in this case, we are given X1, we are given Y, now we are trying to find X2. Again, a generic attack will require 2 to the n operations. So why this is we need such a property? Actually, again, we need it for many different reasons. One example is to check if a file in your hard drive is infected with a Trojan or not. So store the hashes of your files. If the attacker modifies the files, for example, put a malicious code inside them, and can still obtain the same hash value, then the attacker can fool you. But if they cannot do it, so if the hash function is second premise resistant, they cannot do it. So you can check if any of your files are infected or not. Third one is the collision resistance. In this case, it should be hard to find two inputs, X1 and X2, such that their output equals to the same value Y. So you might think that this is the same definition with the previous one, but in the previous one, X1 was fixed, and you were trying to find the X2. But in this scenario, nothing is fixed. So you're only given the hash function, and you are asked to find just two inputs that give the same output. So in this case, you have more freedom, so it is easier to perform an attack in this scenario. And due to the birthday paradox, now a generic attack is somewhat easier, and the complexity is square root of the previous attack, so it only requires 2 to the n over 2 operations. So why do we need such a thing? Think about so let's look at the following example. Assume that a hacker prepares two versions of a software driver for an operating system where X1 is the correct one and X2 contains a backdoor or a Trojan that allows access to the machine. So if they can create such two drivers with the same hash value, then hacker can send X1 to the operating system company for the inspection. Since it doesn't have any backdoor or a Trojan, they will say that this is virus-free. So they will sign this driver, but signing the whole driver is not easy. So they take the hash of it and sign it. So this area is related to digital signatures. But the operating system company signs the hash of X1 with their private key. But since the hash of X2 also is the same with this hash value, hacker distributes X2 to the user, so they may put it on the web. So whenever somebody downloads this X2, which is a driver with the backdoor in it, when they try to install it, the operating system will say that this is a secure file because they will take the hash of X2, which will be the same with this, and they will check that this was signed by the operating systems company's private key. So they will check it with the public key, and the operating system will say that this file is secure to install, which in reality is not. So this is an example where collision resistance is needed. So these are just a few examples, but hash functions are used in many areas in cryptography. For this reason, we call it Swiss Army knife of cryptography. So some of the usages are digital signatures, message authentication codes, pseudo-random number generators, key derivation functions, and so on and so forth. So we use them a lot. So let's see now examples of hash functions and see how we can use them. So assume that you want to take the hash of some input. So this is your message M. You perform a padding like we did in the block ciphers, and you have a compression function in this construction. So this construction is called Merkle-Damgard Construction. Not every hash function has to be in this form, but the initial designs were always Merkle-Damgard constructions. So what you do is as follows. You have a compression function as f. Initially, it takes an input as IV, initialization vector, and the first block of your message. They compress it and produce output H1. If you have more message blocks, now we apply the same compression function, this time using H1 and M2. Then, so H1 and M2, H2 and M3, and so on and so forth. At the end, we produce an output which is, again, a fixed size. So initial designs were always like this. Let's see an example with MD4. This was developed by Ronald Rivers in 1990. Block size is 512 bits. The output length, which is the message digest length, is 128 bits. Number of rounds are 48. So this is the picture of one round. So imagine that you have this picture 48 times. The IV is put here as the ABCD, which are 32-bit values. And the message block is divided into 32-bit parts, and they are fed from here. So these are just modular addition of 32-bit values. This is rotation. Ki is a constant, and Fi is just a basic operation that combines the input B, C, and D, which are just AND and OR operations and so on. So you repeat this operation many times, and at the end you will obtain the output here, and then you will XOR it with the IV to obtain the hash of it. So MD4 is broken. Generating a collision takes a few microseconds. You can also find images, but it requires 2 to the 95 operations, which our computational power would not be enough to perform this many operations. So this was the IETF standard hash function defined in RFC 1320, and it was retired in 2011. It influenced a lot of the later designs. So let's look at MD5, almost the same picture. Now the number of rounds are 64 bits, and there's extra addition here. So they thought that this would be secure enough, but it is also broken. So here's a collision example. This is X1 is a 512-bit input, and X2 is another 512-bit input. They're almost the same, but differences are shown in red. This is in hexadecimal notation. So we have two different input, X1 and X2. But if you compute the MD5 of both of them, you will have the same output here. So this is an example of a collision. Next we have is SHA-1. It was developed by NSA. Actually, their initial design was called SHA-0, and they, I think, added this rotation here, I guess, if I'm not mistaken. So this is SHA-1, but SHA-0 is missing one of these rotations. So it looks really like the MD4 and MD5, but this time the output length is increased by 32 bits. For this reason, now we have another word here, E. And the number of runs is increased again, 80. But again, this is not secure. We have collision attacks for this. Let me show you an example how we use a hash function. So assume that you created a file, a text file, and you put the characters ABC there. If you compute the hash of this file, what happens is as follows. You have the IV here. This message is converted into hexadecimal notation like this. ABC is 61, 62, and 63 in ASCII table. Then we apply the padding, which is we are putting single 1 bit and fill the rest with zeros. So this is why we have 80 in hexadecimal notation. And at the end, we put the length of the input message. So this is 3 bytes, which means 24 bits. So 24 as integer, when converted into hexadecimal, becomes 18 here. So this is the block contains WIs, as in the picture WIs are here. So if you take the hash of this message, we have 8 runs, and at the end of each run, these are the outputs. It continues like this, and at the end, you obtain this output. You write them here, you add them to your initial values, and obtain the output hash function, hash value like this. So this is how a hash function works actually. So we thought that there was a theoretic attack years ago, which required 2 to the 63 operations to break, but this also requires a lot of memory. So people weren't able to find a collision for SHA-1 for a very long time. But then, but SHA-0 was broken years ago because the collision attack requires less operations. But and also SHA-1, a lot of browsers stopped accepting SHA-1 SSL certificates by the end of 2017. And this attack were now possible by the help of GPUs. Of course, the original attack requires a lot of memory, but by using some time memory trade-off techniques, people found a SHA-1 collision. Here is the example from the paper where they announced the first SHA-1 collision. So for this reason, we actually stop using SHA-1, and you shouldn't be using it because in the future you might have some problems. SHA-2 is similar to SHA-1, but this time we have more words here. The output size is increased. And then we have more operations here, and they are defined here. As you can see, they are simple operations like AND, XOR, NOT, etc. And we have some just rotations here. So SHA-2 is secure. But as you can see, all of the previous ones were broken. And actually, this slide explains it better. Since MD4, MD5, SHA-1 are broken, only SHA-2 remained, but it was similar to previous designs. So NIST announced a hash competition to have a plan B. If in case SHA-2 is broken, we can migrate to another hash function. This competition was held between these years. It received 64 submissions, and there were 4 submissions with Turkish designers. And almost every information about this competition can be obtained from this web page. But at the end, Ketchak was the winner of this competition, and it is now named SHA-3. And good thing is that its design is very different than the previous hash functions like MD5 or SHA-1 or SHA-2. It is not Merkle-Damgard construction, but it's a sponge construction. But it is kind of complicated to have a single picture of it. If we want to summarize, a lot of hash functions are broken, and broken ones are MD4, MD5, SHA-0, SHA-1. But currently you can use, we haven't talked about it, but we have RIPE-MD, which has 160-bit output version, is secure. So instead of SHA-1, you can use RIPE-MD. But for larger output sizes, SHA-2 and SHA-3 are secure, and you should be using them, and you should never be using these broken hash functions. Again, in the future, you might, if you use SHA-1, you might have some problems soon, but if you are using MD5, you have no security at all.